So first, a question to the audience, or a couple of questions to the audience. Who has been on FOSDEM 3 years ago? Okay, a couple of you. Who has seen the talk that we have been giving 3 years ago at FOSDEM on this? Okay, just a few of them. Okay, so 3 years ago, I was on FOSDEM 2014, and I proposed an idea to create an open source software platform for autonomous driving systems. And the general idea was, okay, we want to reuse software that's existing in the open source community to build up software platform that's going to be running on an ECU in the car. And this is work that I and two colleagues of mine, that's Tilman Ochs and Daniel Wagner, had been interested in, and we have been working on this for the last 3 to 4 years. And we can now say that we're at some point that we have some first insights, some first results, how the project worked out, how it might continue. Right? So the title on the internet was Success and Failures in Building Such an Open Source Software Platform. I changed the title, make it a little bit shorter, and I changed the word failure to difficulties. Failure is only when you give up, right? So we haven't given up, but there are some difficulties that we still have to overcome. So who am I doing this for? So I'm working for a company, BMW Car IT, that is a subsidiary of the BMW car company. It focuses on software development. We actually consider a vehicle not as something from metal and plastic and so on, but actually just as a very small distributed system that happens to be running on 4 wheels, right? So it's just a simple distributed system, and you can do all the software development that you know in such a system as you would do it in an IT system. We use various open source software. We participate in a few open source communities in our area and contribute back our work in these communities. And this company asked me 4 years ago, so how will the future ECU for autonomous driving look like? And that was our basic motivation in 2013. What's the technology that we're going to use when we want to build such an ECU? And this is what we call a software platform. Right? So if you look into the automotive industry, there's actually, for autonomous driving, you'll have 2 classes of software functions. Software functions. So you have control software and you have cognitive software. Control software is what we have been doing in the automotive industry for 40 years. It's a very simple controller that's running on a low power, low cost ECU. And this has evolved step by step over the years. So the code is getting more and more complex, but it's generally still of the same type. It's a state machine. It has to solve some kind of differential equation, and it is matured over the years to a certain state of art. We use a very static software structure, so you design it once and you never change it again. And you can run it on very low-cost ECUs. On the other hand, for autonomous driving, we're going to have a new set of software functions that are going to be cognitive software. So these are much more functions that you would expect a human to be doing in the past, but now a car to be doing by its own. So you have to perceive the environment, you have to reason about traffic situations, you have to predict how traffic participants will behave, and you have to somehow communicate as well with other participants on the road. And for this cognitive software, you have completely different requirements, different characteristics. It will use dynamic models. It will use algorithms that you know from artificial intelligence. It is rapidly evolving, so you can't just take one technology and say, okay, that's going to be the technology for the next 20 years. You have a dynamic software structure. Things will change much quicker. And you run on ECUs, or you run on hardware that is high performance mainstream hardware. Okay. So there are, in fact, two key use cases that you have to consider when you want to build such a software platform. The one is that you have this high performance computing. This means that we will have, we want to decouple the application software development from the hardware technology, and the hardware technology that we're thinking of is some typical hardware that you would know from desktop computing. So right, we have x86 architectures, we have GPUs, we have FPGAs, we have certain DSPs, we have a DRAM, we have NAND flash, and all of this is in one ECU, and you want to decouple application development from that. A general thing that you also have in desktop computing. Second thing is that we will develop the software, and while the software is actually put into a product, we have to find out what are possible failures. We have to improve the software as actually put in the field. Right? In the beginning, we will have functionality that has to be observed by the driver, but we want to continuously go up and up in our confidence to the point that at some point we can say, okay, the driver is out of the loop. But for that, we have to improve the software over time in a running fleet. And these two use cases motivate a completely new software architecture. So the software architecture that we came up with is roughly as follows. You use Linux as an operating system. You want to use some kind of communication middleware that offers you some kind of dynamic connection of components and the usual patterns of sender-receiver and remote procedure call. So something that you might know from MQTT. And then you have certain functionality that's more or less automotive specific. And as this is non-differentiating, you could do it as an open source software. So our primary assumption was we have a software platform that provides the basic functionalities that you need in ECU, and this is open source because it's not visible to the customer, right? And it's not differentiating. So we do it as open source. On the other side, we have a core business. We want to sell something to our customers, and that would be the usual driving functionality, and that would be kept as our product. But this black and white thinking that we had in the very beginning turned out to be not really true. There are some kind of gray areas. Namely, when you get into the more automotive-specific functionality, we found out it's much easier, even if it's not visible to the customer, it's much easier to have a cooperation that is gated. And this means you want to work together on a software development, but you have certain terms that you have to agree on beforehand so that the cooperation works. The reason for that is that we're considering we all consider the same market segment, We all want to sell cars to the same people, and we don't actually have different possibilities of differentiating within this market when we consider software. So we actually have to make rules and say, okay, if we want to cooperate on these things, this software development, everyone has to contribute to that. And we ensure that by certain contracts. So here are some examples, right? You know open source development, for example, you know the Linux project, maybe you know the Yocto project, let's say tool chain for embedded development. Right, we have a gated cooperation within the automotive industry. That's the AUTOSAR development partnership, and we have core business functions that you can more or less buy in our products. It's like remote control parking or driver assistance systems. So what we had to do is we had to find out where do we place certain functionality of our platform into which of these boxes, right? And as we had these discussions internally and with partners, we've actually found out, well, for the operating system of this platform and the isolation mechanisms, we actually can work together. There's a large market. We can use open source. We can contribute to open source. On the other side, we also imagined that you could do some kind of vehicle-wide software update. And there it turned out that this is a core business of the automotive industry. This is something that might first not seem visible to the customer, but it offers such a benefit in the development and in the services that we can offer to our customers, that it remained a differentiating factor, or is considered still a differentiating factor. So a vehicle-wide software update functionality is in most companies a core business and internally. And then we have other things like model-based development, diagnostics, and the communication middleware that was more or less developed in this gated community. Because for diagnostics and model-based development, the automotive industry is the main user, the main participant of that development. For the communication middleware was kind of difficult. It could have been open source, it could have been the gated cooperation, so it's still open which one it will be. Especially when we look into the communication middleware, this was a very, very difficult task. In the very beginning, we looked into the existing implementations and the existing products that are available, and we saw, okay, there are 3 or 4 choices that you could make, and we would just have to make one. Then we continued the technical discussions and found out, well, they're actually really, from the functionality side, they're very, very similar. And then we had to make the difficult decisions, and it turned out that we had to understand the whole history to understand how the situation emerged that we now have. So in 2003, or around 2004, the AUTOSAR consortium was found, and there was a common runtime environment that's in C, and that was implemented. And it's one standard. There are multiple implementations for that. And from that, in 2011, the SAM-IP protocol evolved. So it's a protocol that works on Ethernet as IP-based and is a de facto standard within the automotive industry for Ethernet communication. From this SAM-IP protocol, 2 new C++ APIs evolved. The one evolved in around 2013. That's a common API C++, developed within the Genevieve community, is an open source product. And in 2015, they started within AutoSAR another API, adaptive AutoSAR communication API. Again, C++, similar functionality, similar feature set. On the other hand, in the robotics industry, they had a development that started in around 2008 and is still ongoing. That's the ROS middleware. It has, again, similar functionalities as the other C++ APIs. And this has built up a huge community in the robotics research area. In around 2014, ROS wanted to reinvent themselves. They wanted to build a new API. So they intentionally chose to have a remaining version of ROS 1 that's ongoing and maintained. And they created a new version, ROS 2, that was based on the DDS standard that has been used in mainly military context. But it was a standard that was at least standardized within the OMG, so the object model group. And now we have this situation that we actually have 5 different C++ APIs. Yeah. So the question is this a problem for the automotive industry or not? And the problem in the automotive industry is that we have a very long tool chain of software development. So there are various companies that have to collaborate with each other so that you get the final product of your software. You have the OEM that integrates it into the car, but he doesn't do the whole software development itself. He has a tier 1, he has possibly multiple tier 1s that he works together with. The tier 1s work together with someone else, tier 2 and so on. So you have a huge group of companies that have to cooperate. So reasonably, they all use the same APIs. And now we have 5, right? So it's clear that you want to have convergence, that you can actually save money and you can quickly come to products. So the question is, how will this evolve in the future? And for the first two, for Common API C++ and Adaptive AutoSAR communication, you could expect convergence because it's within the same industry. It's actually the same development company, right? So BMW is involved in the development of Adaptive AutoSAR, and BMW is involved within the development of Common API C++. So if people within one company can figure it out, it would converge. Right? It is based on the same protocol, and it uses similar terminology. That's already good for people, right? When one person speaks about a channel and the other one knows, okay, channel means this, right? Similarly, ROS 1 and ROS 2 have evolved from the same company, and then convergence is actually intended by design. They wanted to try something new out, that's why they called it ROS 2, but they intend, once it's in a stable state, that they all move the whole ecosystem from 1 to 2. So how about convergence of these two paths of the robotics industry and the automotive industry? And there's at least some indications that convergence could be possible and would happen. So just tell you a few of them. They're actually used within, both technologies are used within the same organization. So if you look for presentations on Adaptive AutoSAR, and if you look for presentations on ROS, you will see that BMW and Bosch have presentations about it, but there are also other companies that use that within the same company. Right? They have complementary strength. Adaptive AutoSAR focuses on a specification. And ROS is actually very strong on the implementation side. They have a wide support for different programming languages, and they have a great tooling environment. Also, we have a possible adoption through the next generation employees. So ROS is used and taught in universities. There are various tutorials on the internet, and people learn that from the beginning. And the automotive industry is, of course, hiring many people at the moment due to this hype of autonomous driving. So they'll find many graduates, and they'll probably come with this mind that they have a certain tool already learned in university. And on the technical side, the API design and behavior is actually very similar. They follow very similar design patterns. They have a slightly different service discovery mechanism, but this is probably something that you could overcome. And they have different terminology. Again, there you would just have to find out if it's possible to come to the same words for the same mechanisms. Yes. So I'll just say a few words to other aspects that we have considered. So I said we would use Linux, the Linux operating system as the basis for this software platform. And when you think about it, if you want to use it for autonomous driving, you have 2 points that you have to address. How do I do software-related? How do I do safety-related software development? And how do I ensure the real-time property of the system? And we have been involved in both these fields. So if you consider what was the state that we started in 2013, we actually talked to people, and they said, well, safety-related software development you do in C, and you use a dedicated operating system. So if you look at this state now, in 2017, there's actually a lot of discussions and plans to do safety-related software development in C++14. So we've moved past this, everything must be in C. And we're working on a Linux qualification, safety qualification for Linux, so that we can use Linux in a safety-related area. On the real-time side, in 2013, the preempt RT patches from Thomas Gleixner were out there, but they haven't been in the mainline kernel. Everyone could use them, but they've never merged into the mainline kernel and had to be maintained out of tree. There was a minimal funding by OSADL to keep this happening, but there were no plans for mainlining. So now in 2017, the Linux Foundation funds Thomas Gleixner and his team, and they're making this preempt RT mainline. And I think if you find him on the conference, I've seen him yesterday, he's probably going to tell you it's going to take 1 or 2 years, and then he's going to be done with that. So what has happened in the last 4 years? Generally, the perception on open source on Linux has changed. So as I had discussions 4 years ago, people were just saying, well, yes, you want to build this software platform based on Linux. Well, Linux is just not good enough. And now, 4 years later, this has changed from, well, yeah, Linux is good, but safety, it's not good enough for safety. And we have now actually moved even to the point where people say, well, Linux is really good enough for safety systems, but we just don't have it proof yet. So once we have that proof, we could actually move on in that step. But the story isn't over, right? We see that there's a lot of work still ahead of us. I mean, the convergence of this adaptive AUTOSAR communication specification and the ROS2 efforts is going to be a lot of hard work. It's still unclear how you would actually create a long-term collaborative model for a safety-qualified Linux so that actually companies can cooperate on a core safety asset and still build their products. And the mainline work on real-time capabilities in Linux is certainly funded by the Linux Foundation, and Thomas Gleixner is working hard on that, but there's still a lot of work ahead. Yeah. So that's my talk. Any questions? So the question was if the ROS software is good enough for production use, right? I presented some work on ROSCON that we would have to, right, if you take the current ROS development, it's not going to be good enough for this software development in the car. The authors of ROS actually confirmed that this is true, right? It was a student project that they had, and it served that purpose. But so that's why they created ROS 2, to actually address all those aspects. Is it good enough for safety? Does it have certain fallback mechanisms and so on? The 2.0 should be good enough, yes. Yeah.